Hi, welcome back. This is lecture 12, in which we're going to talk about mechanical equilibrium and look at examples thereof. So we are going to ask the question, mechanical equilibrium, well, what is it? Let's define the term. We're going to learn an important tool of analyzing forces, something called the free body diagrams, where we show all the forces acting on an object. And we'll do some examples in which forces act in all sorts of directions, and so we'll treat them as vectors and pay attention to their components, and we'll hopefully get very good at that, just because we'll need it so much. And as a big bonus at the end, you're going to learn how to get your car out of a ditch using, well, your bare hand and a piece of rope. Alright, so let's get started. So remember that we said in the last lecture, where we sort of very casually introduced forces, that if you got multiple forces acting on an object, whatever those are, something's pulling with a rope, it has a weight, there's somebody pushing with their hands, there's thrusters attached, whatever forces are acting, if they all add up to 0, remember the net force, maybe we should annotate that. Net force, of course, means the vector sum of all the forces. Hopefully you remember that from the last lecture. So when all those forces that act on an object, when they cancel out, so we've got 0 net force, well then we've got 0 acceleration. And in fact, if we didn't have 0 acceleration, then we would have to have a non-zero net force. So it's kind of like if this, then this, but also if this, then this. Hence this two-way if and only if. Okay, so let's define this term mechanical equilibrium. Well, mechanical equilibrium corresponds to exactly this situation. Object, the net force on which is 0, I guess, funny phrasing, an object on which the net force is 0 is said to be in mechanical equilibrium. Now, I've got to be careful. There's one subtlety here that often gets overlooked, and that is the following. So when something has 0 net force, 0 acceleration, so one option is that the object could just not be moving at all. Might not be moving. In that case, we talk about what's called statics. And in fact, there's a whole sort of field of engineering where you worry about those situations. If you want to build a building or a bridge, well, then you want it not to move. You want it to stay where it is. So this field of statics is kind of big in civil engineering, for example. But in general, we call a situation where an object is just stationary and remains stationary. So 0 velocity, 0 acceleration. We call it static equilibrium. So the static equilibrium is a special case of mechanical equilibrium. In the sense, it's the case that probably first comes to mind. But, and that is the crucial part, that is the subtlety, it's not the only case, or the object could be moving with a constant velocity. Because 0 acceleration does not mean it's not moving, it just means it's not changing its velocity. We've learned about that and spent the last couple of weeks talking about that. So the object is moving with a constant velocity. So either case, 0 acceleration, the net force on the object must be 0. Okay, so now let's just look at some examples to see this in action. So here's my first example. Think about it. Imagine I have some kind of crate. It's very heavy, and it's hanging from a steel cable. Maybe it's attached to a crane or some kind of pulley system really high up. I'm not going to worry about that. And I know that the crate weighs 5,000 newtons. Right now, remember 1 newton was about the weight of a potato. Right? So how hard is the earth pulling on a potato? Well, it's about 1 newton, roughly, medium-sized potato. So we've got a crate of 5,000 potatoes, or maybe it's just some block of steel, whatever it is, doesn't matter. So when we talk about something having a weight, that means this is the force of gravity. We'll talk about that a lot more in the near future. Let's see how to actually calculate the weight of an object. Right now we're given, okay, this thing weighs 5,000 newtons. But it's hanging from a steel cable, and we assume, and maybe I should have said this here, the object is at rest. It's just hanging there. So the question is then, what is the tension in the cable? So when you want to analyze forces, then what we do is we draw what's called a free body diagram. Now to do this is we really just draw vectors emerging from a single point that represents the object, and we draw vectors in the direction of the forces and with the magnitude corresponding to the forces. Now I could actually just draw the forces here, so I'm going to do both right now. So the weight is acting down, so I might draw it like this. And I'm going to draw it at the center of the object, right, starting right here. The tension, right, the tension on the cable, well, it's pulling the crate up. How do I know this? Well, the cable is going up, right? The cable can't push, it can't pull sideways. If the cable is straight up, then it can only pull straight up. So I want to know how strong is the force up. Well, let's say initially I might not actually know. Let's sort of draw something. So I could draw it like this. And then, well, so this would be just drawing the force in the picture. Technically, a free body diagram would be to just, I don't draw the picture in full, I just draw a little point, and I attach the forces to this. And it just allows me to get rid of all the clutter, like this guy here. What's this guy doing in the picture? I don't really care, not relevant. So I'm going to cut it out. I'm just going to draw it like this. Weight, tension. Right, so my first step was to figure out, well, what forces are acting. I assume those are the relevant forces acting. Now, what do I know? I know what the weight is, right? We know the weight is 5,000 newtons, right? We got it from our free body diagram. Up here, right? So this is what we mean by the free body diagram. We might abbreviate this FBD, free body diagram. Okay, so what is the tension? Well, what I know is that the object is at rest. That implies that the net force is 0. Or I can say this as all the forces cancel out, saying the same thing. All forces cancel each other. And that's often the more intuitive way to think about it. Well, if the forces cancel each other out, then the weight's pulling down with 5,000 newtons, while the tension better pull up with 5,000 newtons. So because there are only two forces, they have to cancel each other directly. Tension cancels out the weight. That implies it's also 5,000 newtons and straight up, which we knew anyway. It has to be straight up because weight, gravity, acts straight down. Okay, fairly straightforward. Let's move on to another example. Here is example 2. Imagine there's a physics book, and the physics book is sitting on the table, like so. And the physics book itself weighs 40 newtons. And now in addition, what I haven't drawn is you're going to lean on it. So you push down on it, and adding an additional 30 newtons to the downwards force. Right? So your hand to the hand, you push down on the book. So the question is, what is the force? Well, it says find the force between the table and the book. So these are clearly about these contact forces, the so-called normal forces the types of forces that stop one thing from falling through another. The reason you can lean against walls and stand on a floor without just falling through it. Normal forces, we'll discuss those more in the near future. Right now, we just need to know that they exist. So let's draw a free body diagram for this situation. I could sort of try to add my my forces directly to the picture. Well, actually, I'm just going to squeeze it in over here. So all the forces here are vertical, right? Because the weight is always straight down. And then we're pushing down with 30 newtons. And it doesn't tell us, it doesn't say straight down literally, but it doesn't give us an angle. So if it's just pushing down, we assume this means straight down. So here's my free body diagram. So I'm drawing the object as a little dot. And then there's the weight down. That is, says here 40 newtons. So then another force is going to be the hand pushing down on it. Now, you might be tempted, if you do this as a big picture, to draw the force acting on the surface where it's acting. And there may be times and places to do that, but for the purpose of a free body diagram, we just care what's the force acting on the object. We don't care is it acting on the top or the object as a whole or near the bottom. So we just draw all the forces are coming out of that single point. Now the pushing down force is 30 newtons, so I'm going to draw this slightly shorter, 3/4 of the length. So that's the hand pushing. There's nothing wrong with using non-technical terminology like the hand push. Who cares? We know what it means. Right? What we're going to call it the contact force due to the humanoid hand or something. No, it's silly, right? Hand pushing, 30 newtons. There we go. Okay, so right now, if those were the only two forces, the book would clearly get pushed down, net forces down, we would have a downwards acceleration, which means the book would start moving downwards. Well, that's not happening. The book is clearly at rest. It didn't say so explicitly, but the physics book is on the table. So, I mean, it is at rest. If it were something else, it would really have to tell us, right? Okay, so that means something's stopping the book from falling. Well, it's this contact force between the table and the book. Kind of down here, right? Between us, you can't see it. They're touching. I'll draw a little shadow here. So, down here, well, it's pushing the book up. And so, how big is it? Well, it has to cancel out both of the other forces. So I'm going to call it the normal force. And as I said, we'll discuss the terminology later. Why is it called a normal force? Normal force with the table. Right, the book and the table. They have normal forces, of course, on each other, because remember, it's always a two-way process. But right now, we're just analyzing the forces on the book. Okay. So, well, we can do the math, right? The object is at rest. So that implies that the net force is 0. Or I could just say the forces all cancel out. So the weight and the hand, they work together. So you have to add those. 40 newtons down plus 30 newtons down. Well, that better be equal to the normal force. And so the normal force must be equal to 70 newtons. Again, fairly straightforward. You probably could have just guessed this correctly, not knowing anything about forces, but it's good to make it explicit so we're ready for some more complicated problems. Okay, let's move on. Actually, we're going to come back to example 1 now, but we're going to modify it a little bit. What we're going to do is we're going to assume that again there's a crate on a cable, but now, example 3, you can totally, put it underneath example 2. same situation, but what if the crate were moving upwards at a constant 2 meters per second, right? So here, the crate was just hanging still. The weight equals the tension. Our book was also just sitting still, but now we're going to assume that the crate is moving upwards at a constant 2 meters per second. Well, the answer is, of course, it's exactly the same. Why? Because constant 2 meters per second, right, this implies still zero acceleration. So that means still zero net force. Net force, right? So nothing has changed. It isn't really a new example at all. It's just drawing attention to the fact that the tension equals the weight, whether or not the crate is hanging or moving up or moving down or moving in some other direction, as long as the motion is happening at a constant velocity. If the crate were to, if you wanted it to speed up upwards, like we pull it up, the crane is hanging and we want it to speed up the upward direction, then for a while we need to increase the tension until it has the speed that we want, say 2 meters per second, and then we could just let the tension again be equal to the weight. Right? So only while you change the velocity do you need to change what the tension is in this case, by pulling harder, for example. Right? Okay, so just the subtlety. This of course ties in to what we talked about before, right? Mechanical equilibrium can mean that objects are not moving, but can also mean they're moving with a constant velocity. The math for the force is the same, because in both cases the net force is zero. Okay, so really not much work to do there. We've already solved this. Let's move on. Okay, so here's our next example. Again, we're going to stick with a crate, and again our crate weighs 5,000 newtons. That is a basket full of 5,000 potatoes, or alternatively a bunch of bricks. And we're going to hang it again from some cables, but in this time we have two cables, and they're not straight up, right? But they're at an angle. I make the angle 30 degrees from the vertical. We're going to figure out what is the tension in each of those two cables. And you might really guess correctly that the tension is the same in both of them, because it's just a symmetric situation. And you'd be totally correct and totally justified to say the tension, whatever the tension is in the two cables, it's going to be the same, because the situation is symmetric. It looks the same on the left as on the right. We are actually going to prove that, though, directly. So let's analyze the forces. What forces are acting? There is the weight, and there are the two tensions. Let's draw a free body diagram. So the weight is going to be down, and it's 5,000 newtons, and then the strings, the cables, they can only pull in the direction that they're in, right? Again, if the cable is attached like this, you can only pull in this direction. So that's how they're going to pull. One's going to pull this way. Let's call this the tension on the right. And one's going to pull this way. I'm going to call this the tension on the left. They're probably the same. In fact, they are, but we're not going to assume that quite yet. We're not going to assume it at all. We're going to show it. The angles with the vertical are 30 degrees. So what are those tensions, those two tensions? Well, the object is at rest, right? So zero net force. And that is the case both horizontally and vertically, right? Vectors are forces are vectors. So when there's zero net force, this means zero net force horizontally and zero net force vertically. Of course, you could also analyze the net force in any other direction, so diagonally or something. It still would be zero, right? Because it is not accelerating in any direction whatsoever. but in this situation and many others, but not all, but many others, the situations, it is most useful to analyze the situation by looking at horizontal and vertical forces. Let's define our coordinate system. Doesn't really matter where I pick the origin because nothing is moving, but I need to pick directions. Let's call this X. Let's call this Y. Why do I have to do this explicitly? Well, because before, in the first couple of examples, there were only forces that were all acting along the same line, down and up. Now we have forces acting sort of at angles. So what forces do we have acting in the X direction? Well, in the X direction, we have the weight doesn't do anything because the weight acts straight down. It doesn't pull left or right, so it doesn't feature. But this one pulls to the left, this one pulls to the right, but of course we have to take components, right? Now we know how to do this. So to the left, TL, and then what's the horizontal component of this? Let me just draw it down here, right? I want this component here. Just draw the whole thing, right? TL, TL sine 30 degrees. That is this side here on the top, right? This part here. And that better be equal to TR, well, the horizontal component of this, because this is pulling to the right, sine of 30 degrees, because this is also 30 degrees. Coincidence, perhaps, right? We could have a situation where the cables are at different angles, then I'd put a different value here. So this was TL, this is TR, and here, of course, I care again about the horizontal part. It's this bit here. And those better be equal, right? Because if one of them were stronger, if this one was pulling more left and this one's pulling right, then the whole crate would start moving sideways, which it is not doing. We know that it is at rest. It's something we were told. It's not something we assume, it's something we were told. But from this equation, I can right away see that the tension implies tension to the left is equal to tension to the right. So let's just call those just the tension. So this equal sign, this is sort of like, call these just T. Because I don't want to keep writing TL, TR. There's only one value of tension. Let's call it T, and they are both equal to it. Okay. Now in the Y direction, that's my vertical direction. Well, what force is acting there? That's the weight down. The weight down gets cancelled out by the forces pointing up. That is the tension left and the tension right. But of course only their vertical components. And so we have that the weight is going to be equal to the vertical component of this and the vertical component of this. So let me write it out like this first. TL cosine 30 degrees. I hope you can see why this cosine, because this is the adjacent, or in this case this component here, right, is the adjacent to this angle down here. Plus TR cosine 30 degrees. Now those are the same. So I can just write this is 2 times T cosine 30 degrees, right? Because TL is T, TR is T, they're all one and the same. So that means I can now solve it fairly straightforwardly. So T is going to be equal to 5,000 newtons divided by 2 times cosine 30. Now what is cosine 30? Cosine 30 is something like 0.86. And I think that then makes a tension here of about 2,887 newtons in each of the two cables. Right, that's our answer. That's that's the tension on the left and the tension on the right. So we found our answer. So we needed the first part, we needed the x direction to figure out that those are indeed the same. So that then we were able to solve this one by, oops, what did I do here? Clearly I have gone mad. This was supposed to be a t. So that then, having figured out using the x direction that those are equal, we were able to set this line here equal to this and solve for t, rather than having two unknowns, because, well, we knew they were the same. Okay, so notice that this is bigger than half of this, right? So the tensions don't add up to 5,000, because in a sense, part of each tension is used to cancel out the sideways pull of the other. Right? But their vertical components are each 2,500, so the vertical components together add up to cancel the 5,000. We'll come back to the idea in just a minute. Let's do one more example first. Okay, here's example 5. I'm imagining I'm pulling a heavy sled. Its weight is 600 newtons. I'm pulling it across snow. The snow is fairly smooth, but there's a little bit of friction between the sled and the snow. And I'm pulling it with a constant velocity. So we want to find the normal force between the sled and the snow, like the support from below that stops the sled from just falling into the ground, and we want to find the strength of the friction. So let's start by thinking what forces are acting. Well, for that purpose, we're going to draw a free body diagram, right? So let me see if I can color code them somewhat. So the weight is 600 newtons down. The tension is 70 newtons. Actually, we make this this arrow a bit longer. Let me do it like this, because 70 newtons tension is a lot less. So I'm going to draw it like this. I don't care if I'm exactly right. This is probably still too long, but it'll be okay. Tension is 70 newtons, and I should have, of course, written here that this is the weight. And then the other forces are friction, and there's the support force from below, right? The normal force must be there, because if you were the snow, you would feel squished, right? It's always a kind of thought experiment. Is there normal force? Well, if you were sitting there, would you feel that thing pushing down on you? Yes, you would. So there is a normal force there. So there must be a force up. I can't assume how big it is. So we don't know how big that is. That's one of the things we're trying to find out. And finally, there is friction. And friction has a tendency to oppose motion. Right? So if this thing is going to the right, then friction is acting to the left. We'll talk about friction in a lot of detail down the line. I don't know how big the friction is here. Maybe it's something like this. And when you draw a free body diagram, often you don't know how strong some forces are compared to others, so you draw just the arrow, some appropriate length. You know, we don't know yet how big it is. Okay, so let's analyze the situation. As before, we're going to pick our x and y direction to be horizontal and vertical. Let's just do this. Let me just indicate this here. Y and x, just because I have three forces that are exactly horizontal and vertical, so that I know already, okay, it's going to make my life fairly easy, because I won't have to worry about components of those three. Only the tension makes an angle of 20 degrees. That's the one where I have to worry about its components, because it is at a funny angle relative to the axes. Okay, so which shall we do first, x or y? I suppose, why not start with y this time, start with x the last time around? Analyze this, right? Of course, I should have said this, but we know by now constant velocity means zero net force. Maybe I just write it down just in case. That implies zero net force, because zero acceleration means zero net force. All right. So x direction, right? So in the x direction, there's friction backwards, there's tension forwards, and then there's, well, those two don't do anything. sideways, horizontally, they don't contribute the x direction. So that means because the forces cancel out, constant velocity, and just say force to the left equals force to the right. So I have that friction is equal to the horizontal component of the tension, right? Because the tension is pulling at an angle, well, I need its x component. I could say this is the x component. So that's equal to 70 newtons times, well, this is the angle. I want the adjacent, right? So times cosine of 20 degrees. Make sure again you understand why it's cosine, not sine or something else, right? Make sure you understand the geometry. What is this? Well, we can figure this out. It's just plugging it in. Unless I am mistaken, this comes to 66 newtons thereabouts. So my friction already done. 66 newtons. Right? The thought being, look, if I'm pulling this, right, I'm pulling to the right, friction's pulling to the left. Since we're going at a constant velocity, that means I'm pulling to the right exactly as hard as friction is trying to drag the sled to the left, or trying to slow down the sled. Right? So how far am I pulling to the right? Well, I need a horizontal component of the tension. Okay, so that's done. Very straightforward. And now in the y direction, we've got three forces that contribute. We've got a normal force up, we've got the weight down, and we've got the part of tension that pulls up. Now I actually messed up my color coding here, of course. I'm sure you noticed. If I do color coding, I should get it right. The friction was blue, but purple. In the y direction, so we now have up equals down. So I have the normal force that's just straight up. We're going to add to the normal force the vertical component of tension, because that's what's acting up. The vertical component of the tension, or the y component, I could say. Right? I mean, I could have just said horizontal, vertical the whole time and never introduced x and y. Again, that would have been an okay thing to do. But those two act upwards, while they exactly cancel out the weight. Because if they didn't, then one of them would be stronger. The forces up would be stronger than down, or down would be stronger than up. Well, then the sled would start accelerating upwards or downwards, and would either like take off straight up, or dig itself into the ground somehow. Well, neither one of those is happening. They are complete nonsense. So those forces must cancel out. So now we can actually do the math here. We want to find the normal force. So normal. Of course, we could introduce symbols here, but I don't really feel like it. We can just do this in words. It's going to be the weight minus the vertical component, right? The vertical component of the tension is kind of helping the normal force, if you like. So that is going to be, I guess I'm going to write it out again. Vertical comp of tension. Now the weight is 600 newtons. And then the vertical component of the tension, well, what is this? Maybe we should write it down here. That is 70 newtons times sine of 20 degrees, because I want the vertical component here. What's 70 newtons times sine of 20 degrees? I think that's about 24 newtons, if I'm mistaken. And that implies that the normal force, everything said and done, is 600 minus 24, which in my book comes to about 576 newtons. So just barely a little bit less than the weight. The tension doesn't do very much in terms of pulling the sled up and down. Well, why is that? It's a fairly weak force compared to the weight, but also the angle is fairly shallow, right? Most of the pull happens horizontally. So we can sort of be a little bit intuitive here, understanding why is this such a number that's very close to this one. This one's comparatively small. Just again to check that our answer is plausible, right? That it all makes sense. Okay, so let's do now one more situation. In this last example, I want to talk about how to get your car out of the ditch. So before we go there, let's first notice something. And that's something you can try at home, right? So imagine I've got a little mass, doesn't matter what it is, it could be a little rock or something, and imagine maybe this little sort of hook, little ring there that I can wrap a string through. So the string that comes down, wraps around, goes back up. Now, let's just say, for the sake of argument, this has a weight of 10 newtons. If the string is pulled straight up, like this, then each one's going to pull at 5 newtons. Right? 5 plus 5 makes 10. If, on the other hand, the string is still a little bit sideways, so this is still 10 newtons, now this was 5, this was 5, right? The weight's still 10 newtons. Well, now, these each have to be slightly bigger than 5. That's the example we did before, where we had 2 cables that were, I think, an angle of 30 degrees from the vertical, right? We figured out that that means the tension is slightly bigger because the vertical components have to add up to 10. But because the vertical components isn't the whole thing, it's also a horizontal component left and right, that means the tension itself is bigger. I don't know, maybe it's 6 and 6. Now if you go back to that example with the cables at an angle, and you have an angle that's bigger, it's bigger than 30, maybe 60 or 90, or sorry, not 90, but 80 say, then the tension is going to be bigger. Why is that? Well, in this case, right, so the diagrams for each of them, this gets cancelled out by those two. They add together to make an arrow as long. Those two are half as long as this one, but I've got 2 of them, so they cancel out. In this case here, I've got this, and now I want the same tension upwards, but because the angle is defined to be like this, oops, this is way too steep, obviously, right, these ones here, the dotted lines, the components, they still have to cancel out this. To make that happen, these have to be a lot longer because they're a different angle. This is probably more actually relates to more what this one looks like. Same thing here. So now the question becomes, right, so maybe this is 8 and 8, who knows, right, something like that. So what if I want to hold up my weight, my mass, and I want to have the string run perfectly horizontally? So let's imagine there's a weight and there's a little hook there, and you're wrapping the string through it, and you tie the string up here, you tie the string up here. Well, can I have the string be perfectly horizontal to hold this up? Maybe think something like very light. You can hang some shirts from a clothesline, or from clothes pegs. Well, you can have that pretty much horizontal. However, you can't actually have it be perfectly horizontal. Why? No matter how weak, right, this is, and here it's 10 newtons. Well, I need that to get cancelled out. So if this were like this, like no matter how long the tension is, it can never cancel out this one here, because there's no upwards component. Right? So this situation simply can't work. You can't hang something from a perfectly horizontal string, no matter how hard you try. And the reason is ultimately that the cosine of 90 is 0. That's mathematically the reason, right? Because there is 0 vertical component, no matter how big you make the force. It could be that if this is fairly light and the tension is very large, that you can't see that it looks almost perfectly horizontal, but it's always ever going to be almost perfectly horizontal, never actually perfectly horizontal. And now we can use that idea to get our car out of a ditch. So here's the kind of situation I imagine. Imagine there's a road, maybe here, it's been snowing, it's covered in snow, and your car ended up somewhere in the ditch over here. So I'm looking at it from above. Right, this is your car. You did something, here some tracks. Well, that was foolish, right? You drove too fast. Silly you. Okay, so you're stuck in the ditch. Now, how can we get it out? Well, let's suppose we have a tree over here. And it's a very sturdy tree. And you have a rope. Now, you could tie the rope to your car and you can step onto the road and you can pull and it's not going to budge because it's way too heavy. It's not going to work. You might think, hey, maybe I can build some kind of pulley system around here. Well, maybe that could work, but you're going to struggle to sort of build a pulley system and make that work. Maybe that'll work, but every time you wrap it around a tree, you create more friction, so it'll be very difficult. So here's the trick. Here's the trick. What we have to do is you have to tie the rope from here to here in a straight line. With a cable, whatever it is, right? And then you might say, okay, so what? Well, it doesn't get my car out of the ditch. If you were to wrap it around a tree, you could pull on that, but that wouldn't help you either. You'd still need to pull with a force that's way too big. Let's say we need 10,000 Newton to move the car. That's more than anybody can pull. It's extremely difficult, right? This requires a couple of horses maybe. So what we do is you just go to the middle and you pull sideways. We pull this way. Because what does that do? Well, what we've seen here is this sort of thing, right? This is your rope. Now it's from the tree to the car. Now instead of hanging a weight from it, you are pulling. But by pulling a little bit on here, well, if the rope doesn't come with you, that means it has to get pulled back. So while your rope might then look like something like this, it's just barely has a kink in it, right? So you're pulling this way. There's a tree here. There's your car here. Right, so you're pulling this way. And if I pull with, I don't know, how hard can you pull? Let's say you can pull with 1,000 newtons, right? You need 10,000, but you can pull with 1,000. That's not enough. Right, this is 10,000. This is 1,000. So we need 10 people to actually just pull the car. Well, actually, in this case, what's the tension? Well, in this case, the tension here that's pulling against this point here. That maybe there's a knot there to code for you to grab onto. Well, I can take the components, I can do exactly this analysis, and if this were, say, 1 degree, right, because it's just barely bent a little bit, well, then the tension, the two of them, would be equal to 1/2, because there's 2 pieces of rope, so each one is half of what cancels out this, times 1,000 newtons divided by the sine of 1 degree. Right? Because what cancels out this is this component here of each of those two tensions, right? So I can decompose the tension of the rope like this. Like this, it would look exactly like the hanging weight, except this is seen from above, so the orientation is different, but the geometry is ultimately the same. right? So this thing here is whatever the tension is times the sine of 1 degree. Well, the sine of 1 degree is really darn small. I think it's something like 0.017. You might want to check that. But then times sine of right up here, sine of 1 degree is something like 0.017. It's a tiny, tiny number, right? So what does that make? Well, let me type to the calculator. Let me see. So according to my calculation, this makes around 28,650 newtons. Alright, so that is a lot. That is like 28.65 times the force I applied. The tension here is a lot bigger. If it wasn't, well then this thing would move, right? Start accelerating. But it can't because the rope essentially has a fixed length. So what's going to give? Well, options are the rope's going to break. Okay, you're screwed. Then we might have to do it with like just doubling up the rope so you can have more tension overall. The tree might give. Okay, then you're screwed. You should have picked a different tree. Maybe there's a bigger one right here that'll serve you better. Maybe wherever you attach this to your car will give. Well, now you're actually screwed because you just broke your car in addition to driving it into a ditch. But assuming you're lucky, assuming your car holds, the rope holds, the tree holds, well, you've applied enough tension to pull the car out of the ditch. Now, of course, as you're pulling it, the angle is going to change, and so you're losing this mechanical advantage that you have, right? You're losing this 28.65 factor as this becomes more bent like this because the car's budged a little bit, but it's going to become a smaller number. But you've moved your car a little bit. That's a good start. And once you've moved it, a couple of centimeters, and now the rope is no longer straight. You've lost this great number. It's now a smaller factor. Well, you can just tighten your rope again and repeat until your car is no longer in the ditch. Of course, if you do that, I put up a warning sort of triangle here and here, or at least something else, so that nobody just runs into your rope. Although if they get there, maybe they can help you too. Anyway, okay, so lots of examples here on statics, analyzing static situations, dealing with vector components. You'll get your own practice in, but then we'll be ready to move on to discuss what happens when the net force is not zero. So we can talk about Newton's laws and then do lots more examples in that vein. I'll see you then.